Hello everyone and welcome back to my another video we haven't seen for a while. So this time I decided to create a tutorial series about transformers, and you probably already know what I'm talking about because that shaped the world with the encoder-decoder architecture. And you might recently know that all the time I was focused on some kind of simpler stuff like convolutional neural networks, object detection, stuff with computer vision, or reinforcement learning. So I decided that it's time for me to get into transformers and to understand this kind of field step by step. Because if you grab the transformers and you try to do anything with it without getting deeper into the details, how it works, it will be very hard for us. So I decided that I need to learn everything. So, and the best way to do this is go step by step and understand how all the parts work inside it. So, this tutorial series will be of several tutorials where I'll cover everything from the beginning, the positional encoder, encoder-decoder, the training stuff and data preparation and etc. And lastly, after these several theoretical tutorials, I'll make a tutorial how to create your own, for example, translation, classifier of the languages, or even sound recognition with a transformer architecture. And I'll talk all the benefits of it and negative sides of it, and I'll compare it with convolutional neural networks so it will be easier to understand for us why it works like that. So I have prepared this kind of spreadsheet for myself, so it will be a little easier to show you how each part of it works. So right now I have prepared only the introduction part and the positional embedding layer, and that's what I'll introduce with you today in this tutorial part, and later we'll come with another parts. So basically I'll be filling this kind of spreadsheet and I'll be explaining all the parts with the help of it. And of course I'm not going to publish this kind of details that I mark here for myself, but I'll be writing a kind of detailed tutorials in my text version tutorial, and I'll include all these transformer stuff into my machine learning training utilities library called MLTU that you can install from PyPy. And basically when I'll come to the practical example how I use, I'll create a tutorials with all the code and train models, and I'll upload this for you. And you'll see that it's way easier to train a transformers from scratch than you might think when you know how it works. So basically, let's begin. First, we need to know the table of content. What will be the series, what topics I'll cover with this tutorial series. So, table of content, what will be included into this tutorial series? So, we'll overview the whole architecture in this tutorial and we'll implement the positional embedding layer with all the explanations. That's kind of crucial to understand this part because you must know what comes into the transformer. So in your custom implementations, you would know what you would need to change to the input when you want to apply this to your different tasks. Then we'll cover the attention layers, then we'll implement the encoder and decoder layers by including everything we covered before. Then we'll wrap everything and build a transformer model. I'll show you how to pre-process data for language translation to train a model, and then we'll train it, and then of course we will evaluate by running inference on a new data within the trained and exported models. Well, here will be a lot what to cover. So the first part is the introduction to transformer architecture. So first, we need to know what are the differences between convolutional neural networks. So they are primarily used for image and video related tasks. They excel at capturing spatial relationships and extracting features from input data. CNNs consist of many convolutional layers, pooling, and fully connected layers. And convolution layers use filters to scan and convolve the input data, capturing local patterns and features. Pooling layers shrink the size of the data while keeping the most essential details intact. And fully connected layers provide the final classification or regression output we expect. Well, talking about recurrent neural networks, they are designed for sequential data, such as text or time series. They process input data sequentially, maintaining hidden states that retain information from previous inputs. RNNs are like a brain that remembers past information, which makes them useful for tasks where understanding context is essential, like language processing, understanding speech, and translating languages. But RNNs suffer from vanishing or exploding gradient problems, limiting their ability to capture long-term dependencies. And transformers are a relatively new architecture that gains significant popularity, especially in the field of NLP. And this kind of architecture was introduced in 2017 Attention All You Need paper. Transformers rely on self-attention mechanisms to capture global dependencies between input elements. They can process inputs in parallel, making them highly parallelizable and efficient for training on modern hardware. Transformers have achieved state-of-the-art results in various NLP tasks, including language translation, text summarization, and semantic analysis. But you probably are familiar with that. For example, ChatGPT are the transformer, very huge transformer trained on a huge amount of data. So we'll do the same stuff. And compared CNNs and RNNs, Transformers has several advantages. The main one is parallelization. Transformers can process input elements in parallel, making them faster to train and more efficient on hardware that supports parallel operations. And attention mechanisms. That transformers use self-attention to capture global dependencies in the input sequence, allowing them to attend to relevant context across the entire sequence. This is particularly useful in NLP tasks where long-range dependencies are essential. For example, when we are trying to explain or shorten information from 1,000 or few thousand words into smaller one simple paragraph to give us summary. And this needs to understand all the context. So they use attention for this. That's one win. And of course, Transformers doesn't do SQL processing, unlike RNNs. Transformers do not process input sequentially. They can take advantage of parallel processing and are not limited by the sequential nature of RNNs. That enables faster training and inference on the production side. However, Transformers also have some limitations. They typically require large amount of data to train effectively and can be computationally expensive, especially for longer sequences. Additionally, CNNs and RNNs still might perform well for specific tasks, especially when the input data has a grid-like structure. Or requires sequential processing. But still, CNNs and RNNs have their strengths in image and sequential data, respectively. Transformers have emerged as powerful models for natural language processing, leveraging parallel processing and attention mechanisms to capture long global dependencies. The choice of architecture depends, of course, on the specific tasks and characteristics of the input data. But you might note that transformers require a huge amount of data so they could perform accurately. If you don't have a lot of data, you should prefer moving on with CNNs or recurrent neural networks because they do it better with small amount of data. So now we'll cover the main components of this architecture. So I'll show you an image of the transformer architecture, and that's kind of pretty self-explainable image, but let's go deeper inside of it and understand what it is and what each part does. So transformer architecture is made up of two main parts, the encoder and the decoder on the right. These parts have several layers that use attention and self-attention methods to handle input and output sequences. The encoder changes the input sequence into a hidden representation, and the decoder creates the output using the encoder's hidden representation. The transformer achieves excellent performance on various language processing tasks by combining these two components. So here are a few notes about this architecture. On the left, here is the encoder block. This block takes the input sequence and converts it into the series of embeddings. These embeddings are then processed through a stack of identical layers in the encoder, and each layer consists of two sublayers, self-attention layer and feed-forward layer, as you can see here. Well, self-attention here is called multi-head attention, but doesn't matter. The self-attention layers help the encoder focus on different parts of the input sequence and understand long-range relationships. In contrast, the feed-forward layer applies a non-linear transformation to a hidden representation. Similarly, the decoder also has a stack of identical layers. However, each of layers in the decoder has three sublayers differently from encoder. It has self-attention, Encoder-Decoder, and attention and feed-forward layer. The self-attention layer helps the decoder attend to different parts of the output sequence. In contrast, the encoder-decoder attention layer lets the decoder consider different parts of the input sequence. And the next part is attention overall. That's kind of mechanism that allow the model to concentrate on a specific input aspects when making predictions selectively. In the transformer architecture, attention is used in both the encoder and decoder. It calculates a weighted sum of the input sequence values where the similarity between the query and the keys determines the weight. This mechanism enables the model to concentrate on various segments of the input sequence depending on the particular task. And of course, there is a self-attention. This kind of mechanism is specific type of attention used in transformers architecture. It operates on the input sequence and transforms it into query, key, and value vectors. The query vectors determine the attention weights for each position in the input sequence based on their similarity to the key vectors. The value vectors are then multiplied by attention weights and summed up to create a weighted representation of the input sequence. Well, this representation becomes the input for the next layer, enabling the model to attend to different parts of the sequence and capture long-range dependencies. So from this image, you may notice that there is a positional encoding block added right to the input embeddings. The positional encoding is applied to account for the lack of recurrence or convolution structure in the transformer. It encodes the position of tokens in the input sequence, and each token embeddings is augmented with positional encoding to provide the model with positional information. The positional encoding is calculated using a fixed function that considers the token's position in the sequence and the embedding's dimension. By incorporating this positional information, the model can differentiate between the tokens appearing at different positions in the input sequence. And You might notice that these positional encodings are applied either into encoder and into decoder inputs. In the official TensorFlow transform tutorial, we can find a great visualization of how it works while processing the input data. As you can see that right now it's showing the encoding part, and they all work together to push data into a decoder, and then decoder communicates with the encoder output and previous decoder output and gives us next output. So this is kind of self-explainable GIF, and we don't need to explain it deeper. You simply need to understand how it works in details. So we'll begin by implementing the positional embedding layer into the transformer. So everything is done here in the TensorFlow if I haven't mentioned yet, and I'll show you the image here that you can see where this positional embedding layer is used. So you might see that here is only positional encoding, but if we draw the rectangle here, this kind of wraps up into the positional embedding layer that works with input data as the positional encodings and gives it to the encoder layer. Same relies also to the decoder layer. So the positional encoding function in the transformers architecture introduces the concept of order or position into the input data. Transformers are designed to process input data in parallel, making them highly efficient for tasks like natural language processing. However, since transformers do not have an inherent sense of order, they cannot naturally capture the sequential or positional information present in the input data. In applications like language processing, the order of words in a sense is crucial for understanding the meaning. The positional encoding function is introduced to incorporate the positional information into the model. The positional encoding function maps each position in the input sequence to a vector representation. These positional embeddings are added element-wise to the input embedding, usually a word embeddings, before feeding them into the transformer model. And this addition allows the model to distinguish between words based on their positions, enabling it to understand the sequential structure of the input. The most common type of positional encoding used is based on the sine and cosine functions. This method ensures that the positional embedding have a consistent pattern, allowing the model to generalize well to longer sequences, and it might not have seen during training. In summary, the purpose of the positional encoding function transformers is to introduce position information into the model, enabling it to understand the sequential nature of the input data and effectively perform tasks where the order of elements matters, such as language translation or language understanding tasks. And we will implement this kind of layer. And here's the formula that gives the method to compute the positional encoding. And this might be not that clear for us now, but let's see what it does. So here is pos is the position and y is the dimension. The model is the dimension of the embedding vector. And in other words, each dimension of the positional encoding corresponds to a sinusoid. The position determines the wavelength of each sinusoid and the dimension determines the frequency. The positional encoding is calculated using a sine and cosine functions with different frequencies. And the frequencies from a geometric progression from 2 divided by p to 10,000 multiplied by 2 divided by p. So it's way easier when we might see the implementation in code, and you might see it right now here. And I have this kind of layer, function created that creates this kind of positional encoding. And let's run this and everything should work just fine. So we ran this code and we don't see an output, but doesn't matter. We here define a function that works just fine. So the positional encoding function generates a matrix of position encodings to provide information about the position of each token in the input sequence. This helps the self-attention mechanism transform a model to different between different token positions. The function takes two arguments, the length and the depth, which specifies the size of the input sequence, and of course depth specifies determines the dimensionality of the encoding. To begin, the function creates two matrices, the positions and depths. The positions matrix has a shape of length and 1, like here, and the depth, and contains the indices representing the positions in the input sequence. The depth matrix has a shape of 1 and depth, and contains values ranging from 0 to depth -1, which are then normalized by dividing them by depth divided by 2. So here we divide it by 2. Next, the function calculates the angle rates using the formula 1 divided by 10,000 multiplied by depth, and as you can see from here. And this results in a matrix of shape of 1 and depth. These angle rates are used to compute the angle radians by multiplying positions with the angle rates, and the resulting matrix has the length and depth. And that's kinda it. Finally, the function combines the sine and cosine values of the angle radians along the last axis to create the position encoding matrix. And this matrix has shape, length, and depth. It is then converted to the data type of TensorFlow float 32 using it in TensorFlow. So in summary, the positional encoding function employs a set of sine and cosine waves that oscillate at different frequencies depending on their position with the embedding vector's depth. These oscillations manifest along the position axis, and yeah, of course, we can create the visualization to illustrate the concept. So of course, I have here a code that we run, and the new plot will be generated just for us. Give it a sec. So this visualization aims to help us understand the positional encoding matrix and observe how it varies across different positions and depths in the sequence. It also ensures that encoding values are appropriately normalized and distributed through the matrix. To provide a visual representation, we will plot the cosine similarity between the positional encoding vector at index 1000 and all the other vectors in the positional encoding matrix. But before calculating the cosine similarity, the positional encoding vectors undergo L2 normalization. Then, using the nsum function, the code computes the dot product between the positional encoding vector at index 1000 and each vector in the matrix. The resulting dot product are displayed in a will be displayed in a graph where the y-axis represents the cosine similarity values between the vectors. So actually I already have it here, I ran it before, and here it is. The visualization consists of two plots. The first plot displays the entire cosine similarity graph, while the second plot zooms in on a specific range of the values between index 950 and 1050. Visualization aims to demonstrate how the positional encoding vectors capture the position information of each token in the sequence when the cosine similarity values are high between vectors. It suggests that they are positioned closely along the position axis. This indicates that these vectors share similar positional information, emphasizing the importance of positional encoding in preserving the order of tokens within the sequence. And that's mainly it about this positional encoding. Basically, you don't need to know all the math behind, you simply need to know how to use it, of course. Now that we know how to implement positional encoding, we can create a custom layer that will combine positional encoding with the token embedding. This layer will be used in the encoder and decoder layers later in the next tutorials. So I already have this layer implemented here. So as you can see, we created a positional embedding layer that combines the embedding layer and the positional encoding functions. The class takes two arguments: vocabulary size, which is the size of our vocabulary of the input sequence, and the D model, which is the size of the embedding and positional encoding vectors. This is kind of crucial to the size of our transformer. This layer aims to encode input sequences in a transformer model by adding positional information to the token embeddings. In the constructor of this object, two crucial components are created. An embedding layer is established to convert input tokens into embedding vectors. This is kind of something like vectorizing input integers. And secondly, a positional encoding matrix is generated using the positional encoding function, having the shape of maximum length and the D model. This class compute mask method produces a mask that matches the shape of the input tensor destined for the embedding layer. In the call method, the input tensor undergoes a few mind steps. It passes through the embedding layer to obtain the embedding output. The result is scaled by the square root of the D model. The positional encoding matrix then is added to the embedding output corresponding to each input token, and the encoded input sequence is returned as the final output. That's not like a magic, it's kind of simple. In most cases, when constructing a transformer model, we would create two separate positional embedding layers for the encoder and decoder components. Because the encoder and decoder have different input sequences, they require different positional encoding matrices. However, in this kind of tutorial, we'll test the output of this layer by creating a single positional embedding layer. And this input will use a simple random sequences of integers, because usually when we are working with the text data, we need to vectorize it, tokenize it to convert all the strings or characters into numerical representation. So here what we can do, I already wrote this kind of simple example code that we can run to run this. So let's create this object that we were talking about all this time, the positional embedding, and let's run this kind of function. As we can see, we created a random input tensor of shape 1 to 100 and passed it through the positional embedding layer. The output of this layer has the shape of 1, 100, and 512. This kind of vectorization representation where 100 is the length of the input sequence and 512 is the dimensionality of the embedding and positional encoding vector. And a vector of size 512 represents each token in the input sequence. The positional encoding vectors are added to embedding vectors, providing information about position of each token in the sequence. This allows the model to understand the order of tokens in the input sequence. That's kind of it. And as if I'll show you the architecture of our model, if we will look back to our architecture or transformer, we simply implemented all this input stuff for encoder and decoder, and later we will be reusing this kind of layer for our transformer architecture implementation to construct the whole model. And that's it. In this tutorial, we embarked on the comprehensive journey into a fascinating world of transformers, a revolutionary architecture that has become a game changer in a natural language processing. The step-by-step implementation in TensorFlow and detailed explanation of each component will give us the deep understanding of how transformers work. A notable highlight of the tutorial of this kind of tutorial is to emphasizes on reusability and collaboration. By incorporating all created layers into the ML2 library, the tutorial encourages knowledge sharing and facilitates easy integration of these components onto other projects. And this is kind of crucial because TensorFlow by itself doesn't have this integrated into TensorFlow library. So because I'm creating this kind of machine learning training utilities reusable, and I'll include this kind of custom layers into this library. So you will be able to simply install ML2 from PyPy, and you'll be able to import these layers without constructing or copying for yourself from other repositories. Mainly, what I try to do, I try to cover the whole idea why we use transformers and why they are so game changer that everyone talks about it, and it's pretty hard to understand without trying to implement one by yourself, without understanding what are the challenges and why it requires so much time to train it. You'll be able to understand all of this only by trying by yourself to implement one and train your custom model without using other already completed implementations. This will be way easier for you as a machine learning engineer to grow your skills. And the idea here to encourage you to spend more time on these small details in understanding how each part of transformer works. Without understanding this, it's really hard. It's really hard to adopt the transformers into your problem scope to solve the problem you're trying to. So I'm talking this from my own experience, that at first I tried to implement the transformer without getting deeper into encoder-decoder architecture, without knowing how it works, and it is really challenging to make modifications to this architecture into my problem, and I don't know how to train it, how to run it, and etc. There's many problems comes later that you don't know how to solve, and only by knowing how all parts work you can solve all the problems in your way. So don't hesitate to spend a little more time on these kind of small parts of our transformer architecture to understand, so it will pay off for you in the future as a machine learning engineer, developer, or etc., whatever you do in your life. So that's it about this tutorial. I'm trying not to take this too much time because, well, time is precious and we all save it and we want to get more of it. So I'll end here. Thank you all for watching, and in the next tutorial I'll cover the attention layers that is pretty crucial for transformer, and we'll see you in the next tutorial part. So thank you again for watching. If this was useful for you, like this, subscribe, share this video, and if you have any questions, leave these questions below this video recording. I'll try to respond to them. And thank you again for watching, and see you in the next part. Thank you and goodbye.